specialist at ShapeDiver. Welcome to another episode of this video series where we are creating a table configurator. In the last episode, we looked at texture coordinates and materials, and in this episode, we will make a setup around our table so that it looks more realistic. For that, we will add a ground, we will add some 3D dimensions around our table, and we will also add some shares around our table. Let's get started. Here is our definition as we left it in the last episode. The only difference is this group where we reorganize all our materials and our display components. The only thing that we need to do right now is to give a name to our ShapeDiver display geometry components so that they can be accessed via the API, they can be recognized via the API. This is important if you want to make your models clickable, draggable, to give animation to your 3D models in ShapeDiver. This may not be important if you are just using the plain ShapeDiver solution without the API, but if you want to use the API, then you should always give a name to your components, especially because you're web developers, or if you are the web developer, you will start in the API by adding a code similar to this, where you go API.scene.get, and then inside here, you give a name. This name is equal to the ShapeDiver display geometry name. So in this case, let's say tabletop. So this tabletop name should be available in your ShapeDiver display component. So here we would go and take this component and go tabletop, and then we will do the same with the other ones. So again, this is just important if you want to use the API later and then you want to be able to recognize the geometry that is inside the scene. Okay, now we can start by adding a ground to our table so that it is just not there floating in the space. To add a ground, you can create your own ground. It can be a plain surface, or you can give it a little bit of effect. So we want to get some effect such like this one in this table, where you have this little blurring in the ends of the legs. This effect is created in Grasshopper. So to do that, if we look at the legs in the top view, the only thing that we need is to have some planes around our legs, and these planes, these mesh planes, will contain an opacity map. So to create this effect, we just need our legs position that can be obtained in the apron boundary. We just need the apron boundary points, that's the 4 points where our legs are positioned, and there we're going to create our rectangles. Then we give a dimension to our rectangle, and this dimension has to be the same amount of units in the negative and in the positive direction so that our rectangle is in the middle of our leg. Then this rectangle needs to be converted into a mesh plane, so we go mesh plane. These measures need to have one quad in the width and in the height direction. And then we just use the ShapeDiver display component and the ShapeDiver material component to add some opacity map that we have already here prepared. There are 3 options of opacity map. If we look at this opacity map in the browser, we can see how it works. We can see how this opacity map goes from very white in the middle to completely dark in the ends. And that's what creates the effect that our texture, our ground is disappearing in the space. So if we apply this texture to the opacity channel, so here we have the opacity channel, and then we take this material inside the material input and the meshes inside the geometry input, then we get the effect in our 3D view. So here you can see how the effect is working. Now we again do the same with this. We give it a name. So we go ground, for example, and that's it. That's how you create the ground. The only thing that I forgot here is that you need to move these points, so the base points where the rectangles are, you need to move them 1 unit above the ground. The reason to do that is because if we look at our table in ShapeDiver, there is a plane that is on the ground. This plane is automatically created by ShapeDiver. And if you leave your ground effect exactly in the 0 position in the Z coordinate, then that's going to have a conflict with the plane that is created by ShapeDiver. Because basically you have 2 surfaces living in the same position. That means that there's going to be some flickering of the texture. We don't want that. We want our texture to look all the time sharp. To do that, you just need to move your points 1 unit, so it's just a very minimum unit, so that we can avoid that from happening. So you can go just sum up this with this. That will move our points 1 unit instead, and that will go inside our rectangle component. And that's it. That's how you create a simple ground effect in your 3D models. You can also create other kinds of effects if you want. This one is interesting for us because we're focusing on where the 3D model is touching the ground, but you can create all kinds of effects by using the different channels of the material component. So you could create a texture component where you have grass or you have some wood in the ground. So the next step is to create some 3D dimensions to our table. If you go to the display tab, then you will find some dimensions available by Grasshopper. However, ShapeDiver doesn't support them. We do support the text tag and the text tag 3D component, so we will use those instead. We already have a cluster prepared, which creates the 3D dimensions from scratch. You will be able to access this cluster in the definition that will be available down in the description. The base thing that we need right now is the base curves for our dimensions, to the length of our table, the width of our table, and the height of our table. So to do that, we just need, of course, those 3 dimensions from our parameters. So we take here the table length, width, and height. We will create the base points. So we'll go construct point. We need our length and our width to be half of it. So it will be x divided 2. So in this case, we need the length in the x coordinate, the width in the y coordinate. So with that, we have our base point here. And then we will move this in z, our height. So with that, we can create the line, the baseline for our height dimension. Now we can mirror this point in the YZ plane, and that creates our 2 base points for our length dimension. Now we just need to mirror this same point in the XZ plane. And that will give us the baseline for our width. Then we merge these 3 lines, so we have height, length, and width. We merge them. That will be our base curves. Then we need to give a dimension offset, so how much this baseline will be offset, where the actual dimension will be displayed. So we will use 100. Then the text size we can give to 50. Text base plane, so in this case the base plane of width and length are the XY plane, because they are in the horizontal plane, but the height dimension is actually in a vertical plane. So we need either the XZ or the YZ plane. So we know that the first one is the height, so that will be the XZ plane, and then the other ones that are horizontal will be the XY plane. We merge them again into a list. That will be our base planes. Then we need text format. Text format is if you want to add, for example, the dimension number and then something else. So for example, 3000, and then you want to add millimeters. In this case, we won't add anything. We just have it as 0, so it will just show the dimension and that's it. Then we have mark size. So we have 2 styles of marks. We have arrows or lines. In this case, we will use an arrow. So 0 for arrow, 1 for line. And the mark size, let's say 15. Let's see how that looks like. So we go data to see how that looks, what is the result. So the only problem here is with the width dimension. Based on the line direction is where the line will offset. So in this case, we need our width to have the opposite direction. We will flip our A and our B, and then that will give us the correct position of our dimension. And then we can either check this as a 3D text, so if we go true, we will see the text as 3D positioning, or we can go with 2D text, that in this case will be using the text tag component. So we use the text location in the location input and the final text in the text input. And then that gives us the dimensions as 2D tags. The advantage of having them as 2D tags is that then the dimensions are all the time facing towards the camera. So they are all the time aligned with the camera, so they are easier to read. In this case, the only problem that we have right now is with the width dimension again, because our dimension should be actually rotated 90 degrees, so it is oriented with the line itself. So to do that, we just need to rotate our plane. Rotate plane. Rotate it 0.5 multiply p, that means 90 degrees. So now we have everything aligned in the correct way, in the correct plane, and then we can again go these to false. So these 3 dimensions are the ones that let us create these holes. The hole that is where the dimension is displayed. So that's why it is important to have the correct orientation of our text and the correct size, so that our 2D tags have enough space to be displayed. So if we go again 3D text to false, and then we display this again, then we can check the final dimensions. We also have other 2 inputs in our dimensions cluster that are the compute squid and squid color inputs, and for that we get an output also called squid instructions. You can create images with it, automated images. However, we want touch this in this tutorial. We will look at creating images for this table in another tutorial. For now, we just created these dimensions, and then we just need to display them with the ShapeDiver display component. Then we just use the simple material component. We need a color for our dimension, so that color will be black. So this ShapeDiver display geometry component shows the lines and the arrows, and this other one shows actually the 2D tags. So we can put this inside our color input. So we have both in a black color. Again, we give it names to our components, so that again this is recognizable via the API if we want to access this information via the API. So now we have our dimension displayed, and the last thing that we can do to make our table look more realistic is to add some shares around it, so that the client, if they are going to use this table for a dining table, for example, they can see how the shares are aligned around this table. I had already downloaded a share from the internet. I downloaded this and I internalized the mesh and oriented in the correct way. So if we check the base geometry of our chair, so we have the chair apple story, that's this part that is going to be a textile material. Then we have the chair mesh itself, that is going to be the wood material, and then we have the chair base, that is the same thing that I did with the base of our table, that we created these simple planar meshes so that we could create this blurring effect. I want to do the same for the chair, so that's why we have it also here. So we want to orient this chair around our table. To do that, we have already prepared a definition, a little definition here, which includes moving our chair and also orienting it, so rotating it so that it is in the right direction towards the table. If we check the inputs of this group, we have the table length, the table width, the final offset. The reason we have our final offset is because we want to calculate the position of our chairs, having into account the offset that we have between the tabletop and the actual apron. And then finally we have, of course, the space between seats, so how much space each seat can have to be positioned. So in this case we have 600, and that gives us as result that we can have 3 chairs in the length and 1 chair in the width. 1, 2 and 3. We have 3 spaces in the length and a single space in the width. And what we need to do is to calculate the points where these chairs will be positioned. So those points will be in the middle of these spaces. 1, 2, 3, and then here we have 1. So that's basically the result that we get here at the end, where we have these 2 points constructions here. So we have this one that gives us the 3 points in the top and in the bottom, because we want to position our chairs in both sides of our table, and the same happens to our width. We have 1 in each side. And the last thing that we need to do is to rotate. So here we have the rotation that are available, because we have here in our output of this merge component, we have 4 branches, 2 that start with 0, that means the length branches, the ones that are positioned in the length, and 2 that define the width branches. The width branches both are positioned in this way, but the length branches are positioned in the other way. That's why we have this rotation component here. Then we take the transformations of moving our points and of rotating them, and we compound them, we join them. So each chair is moved and rotated. So at the end we have 8 transformations, so we have 8 chairs in total. And then we have 2 options to use these transformations. We can merge our geometry here, our meshes here, and then use the native transformations component that Grasshopper offers, transform. So we input our base geometry here and our transformations in the transformations input. We need to graph this, so then we make sure that each of these meshes gets transformed, in this case 8 times. So we graph this, and then we input this transformation in the transformations input, and then we have our final result. So if we check the 3D view, we can see all our chairs in the right position. Now the problem of doing this is that then I need to send all of these chairs geometry. That means that we are sending more than 8,000 vertices and more than 4,000 faces. So it's not a huge mesh. However, these chairs are just for visual purposes, which means we don't want them to take any of the computation time, any of the loading time. So to make this even more efficient, we have a C# script, which is similar to the one that Grasshopper has. But what it does is to input these transformations inside the chair's geometry as metadata, and then this metadata is sent to ShapeDiver, and then ShapeDiver just inputs a single chair, and then in the viewer in ShapeDiver, it will apply the transformations so that our chairs are shown as they are shown here in Rhino. But again, the difference is that now we are sending just a single chair instead of sending the 8 complete chairs to ShapeDiver. So if we input this into the geometry, as we did with our other component, and then this into our X form, then we have as output the same amount of meshes, one for the chair upholstery, one for the chair itself, and one for the chair base. But the difference is that now they contain metadata, the transformations data. That is the one that is going to be sent to ShapeDiver. So if we input here the display component of ShapeDiver, this component already can read this metadata and show our chairs in the right position. And then here, because we have a tree with 3 branches, that means that we're going to apply 3 different materials, as we explained in our last episode. So if we go to the ShapeDiver material component, then we have to create 3 materials for this. One is going to be the upholstery one, so we want to add some textile. That textile can come from our ShapeDiver simple material. We can put here as material index our textile index. Our textile index, if we go to our material presets database, we have it here. Default fabric is 700. So that will be our first material. Then our second material will be the chair itself, so wood. In this case, we can use the same wood that is being used for the tabletop. You can decide how you want that to be designed. In this case, we're just going to use the same one that is being used in the tabletop. And then the last one that we need is the chair base mesh. So that will be the same that we are using here. We are going to use the same URL for our base planes. So the base planes are the ones that create this blurring effect in the end of the legs. So we input this into the texture, input this into the roughness map, and this one into the normal map. And then we create another one that is going to use just an opacity map, and that's it. Then we merge these 3 materials. And these 3 materials are the ones that are going to be used in this display component that contains our chairs. And that's it. That's how we have a very realistic setup with our chairs around it. We have this blurring in our ground that gives more depth to our model. Now, the only thing that we need to be careful here is that we need to give a color to our blurring. Right now it's white. This should be a dark color. I'm gonna go for a complete dark so that the effect is visible. Also, we want to do the same in our ground. So again, we have here white, so this should be black. Then don't forget to give a name to the component. So here we will have chairs. And then if we check here again our input and then we change this space, we can see how it starts to change dynamically. So if we go 650, for example, then we check that our table now can only fit 2 chairs in the length direction instead of 3. If we were to change the dimension of our table, so we go instead of 2000, we can go to 3000 of length, then we can check that now our table can have 4 chairs in each side. And now what we want to do is to make this displaying of chairs something optional, because it's just a visual help for the customer to see the product. So for that we are a Boolean toggle. Then we call this show chairs, and then we can use a filter component, and then this filter will break the code in one part here of our chair transformations. When we break this code, this means that our transformations are never calculated, never created, and therefore our chairs are not shown. So we put our filter here in our base dimensions, so we change all of this into our filter, then we put this into the 1. Then you can see that here our chairs are no longer calculated. We still see 1. That's because we need to also use this show chairs toggle in here so that our meshes never go into the C# script. So we go again filter. We put these meshes inside our true input. We put the filter inside our geometry. Then don't forget to input the toggle inside our filter. And there we don't have any chairs. But when we go to true, then all of our dimensions go through our chairs transformations calculation, and then our mesh also goes through our C# script. This is the way that you can hide any geometry in ShapeDiver. You just put a filter in front of one part of the definition where you want to break it so that something is not calculated and therefore is not created in the viewer. The same we want to do actually here with the dimensions, because the dimensions are also something optional. We don't want them to be shown all the time. We want the client to be able to choose whether those dimensions are shown or not. So we use again the filter component. And then here we can, for example, break it here where we have our base construction point. We can put this inside our filter. And then there is where our baselines will never be created. So if I go false, then our dimensions are not shown whatsoever. If I go true, then we see the dimensions again back there. So now we are ready to upload our model in ShapeDiver and see how it looks. We have already our model with texture coordinates, with materials, with a good setup that improves the realism. So in the next episode, we will upload our model to ShapeDiver so that we can see the final result, and we can also tweak some settings in ShapeDiver, such as lighting, background color, background image, camera settings, etc. So if you don't want to miss that out, don't forget to subscribe to our channel so that you get the notification about the next video. And if you like this video, if you learned something new, please click on the like button down below. So thanks for watching and see you next time.